Hello chemistry students, today we are going to talk about the last couple of calculations that are important in chemistry that now that you know how to do stoichiometry and you understand the concept of the mole are doable. And so we use these calculations a lot in lab when we don't know the composition of an element or if we don't know the formula, and because a lot of times, since you can't see the atoms, we're unable to figure out what the compound is. So we use a couple different things. Today we're going to talk about percent composition, and this is simply going to tell us the composition of a compound. Now we can look at the mass, usually from mass, or you can look at the formula and figure out exactly what percentage of each element it is comprised of. Okay, so we can go from mass or formula, and it's just finding percents of elements in a compound. Okay. So this is important when we are looking, if we have mass, if we want to look and try to find what the formula is of something and we just know the masses, or vice versa. And I'll do a couple examples to maybe help you understand this concept. The other thing we're going to do is called empirical formula and molecular formula. And these are calculating what the formulas are using the percents that we find here or using masses. Okay, so empirical and molecular formulas are it's just finding the formula of a compound. Okay, because we know at this point that atoms are so small we can't just look at something and know what it is. So we have to use calculation, we have to use machines that give us percents and to try to figure out what these things are. So let's go ahead and try an example of the first one, this percent composition. Okay, so this is percent composition from mass data. So this is something maybe we have a balanced chemical equation, and we can calculate the mass using stoichiometry of different elements. So it says you have a 13.6 gram sample of a compound containing magnesium and oxygen, and it's decomposed into 5.40 grams of oxygen. Okay, so it wants to know what's the percent of magnesium and oxygen in this compound, or at least of oxygen. Okay, so we are going to be using mass. Okay, mass on the periodic table. In further chemistry, we can actually start using this percent composition data as a conversion factor to help us solve stoichiometry problems that we don't have maybe the mass for, like a given mass. We can actually use this to help us with that. Okay, so this all kind of ties together at the end. We're not really going to get into it here, but if you were to take advanced chemistry or chemistry in college, you would see how all of this fits together. Okay, so this first example, let's go ahead. We have 13.6 grams of the compound. We don't know what the compound is. We don't know if it's magnesium oxide or we don't know if it's a different compound. Okay, and then we have the mass of oxygen. So this is of the compound. And then we have the 5.4 grams of oxygen. Okay, so what we need to do is first try to find out the mass of magnesium, because it's the only thing we don't have. Now sometimes you might have the mass of both the products and you have to add them together to find the compound. In this case we have the compound and we have oxygen, but we don't have magnesium. So we're just going to subtract these to find the mass of magnesium. Okay, so if we subtract those, we get 8.20 grams of magnesium. And what we're going to do is we're going to take the formula for percent composition is mass of element over the mass of compound. Okay, And so we're going to use our first one. Let's do the percent of magnesium, and we'll do the percent of oxygen. So you have to have both of the masses of both of these, whether you have to add or subtract. You'll always be given two sets of data. So if we were given those two, we would have added them together to find the compound, because you need all three masses to do this. Okay, so the mass of the compound goes on bottom. So we know that's 13.6 grams. And the mass of magnesium goes on top. So we do 8.20 grams of magnesium on top. And if we divide that out, we get 0.603, times that by 100 to get a percent. So that moves the decimal over 2 times, so we get 60.3%. Okay, so we do the same thing for oxygen. Is 5.4 grams over 13.6 grams, and we get 0.397, times that by 100, and we get 39.7%. Now, you would think that this would just correlate exactly with the number, but you got to remember these are different weights, so that doesn't necessarily mean there's more magnesium necessarily. Now, these percents always need to equal 100, which they do, so we know that this is our percent composition. So 60.3% of magnesium and 37.7% oxygen. Okay, so it's a pretty easy concept. This is just all you do with it is just divide. The hardest part is finding the third element or the third piece of information that you need. Okay, so let's go ahead and try a more difficult one, because when it gives you the mass, that's pretty easy. Now, this could be turned into something more difficult if I would ask you to do this after a stoichiometric problem, okay? Because you would have the grams, and then I could ask you the percents of them in the compound, okay? And so let's go ahead and try a little different one, and let's do the percent composition from a formula. Okay, so this one we're going to use propane, and propane is C3H8. That's propane that you grill with during the summer, which is very close now. And what we're going to do is we're going to calculate the percent of each of these. Now you could say, oh, that's going to be 30 and that's going to be 80, but first of all, that doesn't add up to 100. And second of all, the weights of these are really important. Okay, so let me show you how that works. So what we are going to do first is we're going to get the mass of carbon in 1 mole of the compound of propane, and then the mass of hydrogen. So since there are 3 carbons, we would take 3 times 12.0011, and that would give us the mass of carbon in this compound. So we know that that's just around 36.0 grams of carbon. Okay, and we're just assuming it's out of 100 here. And then we got 8 of the hydrogens, which is 1.00795, and that gives us 8.01 grams of hydrogen. Okay, so once you have the grams from this, now we can calculate the grams per mole of this, which is, we added up 3 carbons plus 8, if we added this up, it would give us right around 44 grams per mole of this. And now that we have all of these, we can go ahead and calculate the percent composition. Okay, so remember that is the mass of element over the mass of the compound. Okay, so we're just going to take 36.0 grams of carbon, divide that by 44 grams of C3H8 propane, and we get 0.818 times that by 100, and we get 81.8%. Now, notice that was the smallest of the numbers, and it's 81%. Okay, so the next one we have, let's do it on top here, 8.01 grams of hydrogen over 44.0 grams per mole of the C3H8. And if we do this, we get 0.18. Times that by 100, and we get 18% hydrogen and 81.8, so 0.2% carbon. Okay, so you're just using these numbers and calculating molar mass for each. Okay, so again, not too difficult. Now, this leads up to this empirical formula and the molecular formula, so we actually work backwards. So once you have your percents, okay, so if we still don't have that formula like we didn't have in the first one, now we can go ahead and from the percents that we calculated, we can calculate what the formula is, which is really important. And we have to use the mole to do this, so we use 25.9%, okay, or we could have done this, we could have carried on with our first one. First example, and used our percents from the first example and calculated the amount of, or the empirical formula from that. Okay, so we're going to use these percents and we're going to assume it's out of 100%. Since this always equals 100, so we're going to assume it's out of 100 grams. So when you see a percent, you can automatically turn it into grams. So this is 25.9 grams of nitrogen, and this is 74.1 grams of oxygen. Okay. And so now we are going to use the mole to calculate the formula. Okay, so we get grams of nitrogen. So the only place I can find grams of nitrogen is on the periodic table. And 0, 0, when the cursor goes, 6, 7 grams of nitrogen over 1 mole of nitrogen. Oxygen is 15.999 grams of oxygen over 1 mole of oxygen. Okay, so now we've taken both things into moles, and we get 1.85 moles of nitrogen, and we get 4.63 moles of oxygen. Okay, when in doubt on a problem, take it to moles, because moles is what you can work with. So we did this in our limiting reactant, and then we do this to find the formula as well. So now we have the second step here, and all you have to do is divide by whichever one is smallest. So since 1.85 is the smallest, we would do 1.85 moles of nitrogen over 1.85 moles of nitrogen, or just 1.85. We just pick the smallest one, and that's obviously going to give us 1 mole of nitrogen. Okay. And the second one, we'll do the same thing. We'll do 4.63 moles of oxygen over the 1.85. And this is going to give us 2.50 moles of oxygen. We can't have 2.5 moles, so 1 mole of nitrogen, we have to get a whole number here. And if we have 2.5 moles of oxygen, what is something that we can multiply both of these by to get a whole number? So if I times this by 2, I can get 5 moles of oxygen. Multiply this, always has to be the same. I can get 2 moles of oxygen. So that makes our empirical formula N2O5. Okay? Now, this is the empirical formula. To make sure that it's the molecular formula, you have to compare it to the molar mass. Okay? So here's the molar mass. If we take the molar mass of this, we would see that it is 56 grams. So we know this is also the molecular formula. Now, if your molecular formula is 2 times greater, then you would have to figure out which of these, you double this maybe, so N4O10, and your book does an example of this on page 312, if you would like to see another example of how to calculate the molecular formula when the molar mass isn't the same.